Welcome back to chemistry. I promise you I'm going to try my hardest to keep this video short and sweet, as it's just a review of the ocean carbon equilibrium gizmo that we were supposed to have done during class last Friday. So the parts that I'm going to focus on in the gizmo are the data analysis and data interpretation and the pH chunk. So I'm going to start with the analyze results part. In case you forgot, there are 3 pieces of data that we were collecting. It included what was the amount of carbon dioxide in the atmosphere. The DIC stands for dissolved inorganic carbon, which were the carbonic acid, bicarbonate, and carbonate ions, the concentrations of those, as well as the amount of calcium in the ocean water. So this one tells us that based on the graph, the amount of carbon dioxide since the year 1995 has continued to increase. They're asking us to make a prediction, what we think is going to happen to that CO2, and ideally you should have said increased, which would be the correct answer. So when we add that data to the graph, notice that it continues that trend line. Carbon dioxide is increasing. Now that makes sense to us because we constantly are burning fossil fuels and humans are the worst, and we're just like adding a bunch of carbon dioxide to the atmosphere. All right, so that makes sense. Now we get into the dissolved inorganic carbon data. It says, before adding data to your graph, make a prediction. What do you think is going to be happening? Well, historically, if we look at the orange trend line, we're seeing that since 1995, the amount of dissolved inorganic carbon molecules has increased, right? That's what this orange trend line is showing. So if we were to make a prediction for the next 5 years, we would probably also say that it has increased, which would be the correct answer. Then we look at the amount of calcium in the ocean. And this one, looking at the trend line, the green trend line, this one looks to be staying just about the same at about 400 parts per million. So our prediction here would be that it's probably staying the same. Now, you might be thinking here, well, why did the carbon dioxide one go up and why did the inorganic carbon go up, but calcium stayed the same? And let's just pause here and just think about that real quick. We know carbon dioxide was going up because I mentioned we're burning fossil fuels, right? So that trend just makes sense to us that that is going to be happening. But when we look at the DIC, or the dissolved inorganic carbon molecules, why is that also going up? Well, where are those molecules coming from? Well, they're coming from the fact that carbon dioxide in the atmosphere is dissolving into ocean water, right? Carbon dioxide plus water is creating that carbonic acid. That's one of those DIC molecules. Carbonic acid can dissociate in water so that it creates bicarbonate and a hydrogen ion. That's another DIC molecule, bicarbonate. Bicarbonate will release a hydrogen ion again to create those carbonate ions. Again, carbonate, another DIC molecule. So it would make sense to us now that we kind of think about that carbon dioxide and all of those other carbon molecules, we would see an increase in their concentrations. But then why would calcium be staying the same? Well, if we think about it, where does calcium come from in this whole problem? Does it come from the atmosphere? No, it's coming from whatever has been in the ocean this entire time, right? So if we started collecting data in 1995, the amount of calcium that we measured then, well, we haven't added a whole bunch of calcium. We haven't taken a whole bunch of calcium out, so the amount of calcium should stay the same. All right, let's continue our investigation now that we've kind of made sense of that. We go into the data interpretation part, and we are going to look back at the mussel shells. It says that mussels need dissolved calcium carbonate to make their shells, meaning if the concentration of calcium carbonate is too low, the mussel shells are going to erode away. And the flip side, if there's not enough calcium or carbonate ions, either one or both of them, then we won't actually be able to make shells. All right, so it's a two-folded problem there. Either we have mussel shells that are eroding away because we are needing to replace calcium carbonate, or we can't actually build the shells in the first place because we don't have the ions. So what are the correlations between the data that we measured and mussel shell erosion? So the first row of data here tells us the percentage of shell erosion. Remember, back in 1995, there was about 10% erosion, which some erosion is normal because calcium carbonate is soluble and will dissolve, like that's normal. But recent years, like 2020, it got all the way up to about 40%. The next row shows our DIC, remember, dissolved inorganic carbon molecules like carbonic acid, bicarbonate, and carbonate ions. So looking at the numbers there and looking at the graph, we see that that has increased. So they're asking us, is there a correlation between shell erosion and DIC? The correct answer would be yes, because they're both following a similar trend that as one increases, so does the other one. The next question says, is there a correlation between shell erosion and calcium? There is not, right? We're seeing an increase in shell erosion. Calcium hasn't changed at all, so can we really contribute shell erosion to calcium? Well, no, because calcium hasn't really changed. The last question is there a correlation between shell erosion and the amount of carbon dioxide in the atmosphere? Again, since they're following similar trends, then we say that they are correlated. Now, I want to take a pause here and tell you that there is a huge difference between correlation and causation. Correlation means two things are happening at the same time. They're following a similar trend. Causation would mean that because the amount of carbon dioxide is increasing, that's why shells are eroding. Now, eventually we're going to come to figure out that there is a causation, but just looking at flat data on graphs like that, all we can assume is a correlation, not causation. All right, so the next step is looking at the specific concentration of carbonate within those dissolved inorganic carbon molecules. It says that mussels need both calcium and carbonate ions to make their shells. And it says that calcium hasn't changed. Remember, that concentration hasn't changed because we haven't added calcium, we haven't taken calcium out of the system, so that amount's changed. What's changing is the amount of carbonate ions. So to determine the amount of carbonate in the ocean, we are going to use both the DIC measurement and the ocean's pH. It says, use the reaction equation above to answer the question on the relationship between pH and carbonate concentration. Now listen carefully, because this gets where your brain wraps around weird ways. Would a decrease in pH mean an increase or decrease in carbonate concentration? If we break it down, a decrease in pH, we think to ourselves, all right, pH numbers are getting lower. That would mean that we're becoming more acidic. That would mean that we're increasing the amount of hydrogen ions, right? So now we got to think about Le Chatelier's principle. If we're increasing the amount of hydrogen ions here, which way is that going to drive the reaction? If we're increasing hydrogen ions, we want to use them up and get rid of that increase. So we're going to drive the reaction to the left, and we are going to want to create more bicarbonate molecules. Now, as we're doing that, what's happening to the amount of carbonate ions? Well, if we're trying to use up all those extra hydrogen ions, we're going to be using up carbonate ions. So we would expect that there would be a decrease in carbonate concentration. And then we'll go to the next one, whatever it tells us to go. Okay, perfect. So now we know that carbonate is decreasing because the ocean is becoming more acidic because there's more hydrogen ions around. We measure the pH. It's going to end up being 7.95, which follows the trend that the pH is decreasing or we are becoming more acidic. All right, click to continue. All right, so now that we know that the pH of the ocean is 7.95, we can use this graph to figure out exactly how much carbonate is in the ocean. It's going to ask you to use this graph to figure that out. And we said, all right, if the pH is 7.95, it bumps up with the trend line here that says our percentage of carbonate is 10%, which that's a legit number. There's research out there that says that that's it. All right, so now we go to findings. So which of these statements are supported by the data? And you can select more than one. So the first one says did carbonate increase because the carbonate and bicarbonate and carbonic acid, the DIC molecules, increase? Again, we can't really have causation. They're following the same trend, right? They're both increasing, but can't really say causation. Did carbonate decrease because the pH decreased? Probably, right? Remember we did that slide that said, I think it was pH versus carbonate. Because pH decreased, that means that we were increasing the amount of hydrogen ions. We were causing that reaction to run in the reverse, and we were going to be using up some of that carbonate to recreate bicarbonate. So that one would be correct. Has the pH decreased because carbon dioxide has increased? Yeah, right? If we increase the amount of carbon dioxide, then we're going to be creating more carbonic acid, which is releasing more hydrogen ions into the ocean, which is causing the pH to decrease. So that one would be yes. And then the last one, did the DIC increase because the pH increased? Well, this one's just a lie in general because the pH didn't increase at all. We're actually becoming more acidic. So we hit submit, and those are the two things that are correct. All right, so we're going to actually stop there. These big ideas we're going to really hit home one more time in the afternoon. I apologize that this video is a little bit longer than I wanted, but I went fast and I tried to keep things short and sweet. So email me if you have any questions. Otherwise, we'll see you in the afternoon time.